y2m plus 1 are independent. The PDF is given as such, as shown in the equation. If we find the determinant of both CA and CB, as it is a matrix, both the values of the determinants of CA and CB would be equal. If we put out these values in the optimum rule of ML detector, if this value is greater than this value, then X estimate is equal to XA, else X estimate would be equal to XB. If we put all these values of CB and CA in this equation, we will get this equation. If we further simplify this, we will get this rule, which is basically if y2m square minus y2m plus 1 square is greater than 0, we have X estimate is equal to XA and X estimate is equal to XB. So as I told you before, that the detector we have to make does not have any information about the phase of the received symbol Y. So in this equation there is no phase information used. So just the amplitude square values at two sample intervals is compared. This simple rule is also called energy detector or square law detector. If we plot the sample points on the x-axis and y-axis, you can draw a point y on the plane. The projection of these points on the horizontal axis is given by y2m, and the projection of point y on the vertical axis is y2m plus 1. So a very clear decision boundary can be made as shown here in this graph. So wherever this y lies in the region specifies what would be the values of y2m squared and y2m plus 1 squared. Now in the next phase we will calculate the probability of error. The probability of error for a given h is equal to the probability of XA into the probability of error given XA plus the probability of XB multiplied with the probability of error given XB. As we assumed before, we are using maximum likelihood detector and binary phase shift keying. We only have two possibilities. So a priori probabilities are assumed to be equal, and due to symmetrical nature of this probability distribution function, the probability of XA is equal to probability of error given XB. From this we can calculate the probability of error is equal to the probability of error given XA or the probability of error given XB, as both would give the same result. So given XA is equal to X, given X is equal to XA, y2m square would now have distribution of exponent with argument a square plus n naught. Similarly, y2m plus 1 square would have a distribution of exponential with argument n naught. This is inverse of SNR. So this is also inverse of SNR. If in both cases the SNRs are a square plus n naught and n naught respectively. So by calculations shown here, we get the PDF of both y2m plus 1 square and y2m square are calculated here. The probability of error can be calculated by taking double derivatives as shown here. If the derivatives are solved, According to the equation shown here, the probability of error would now be equal to some function of SNR. We get the value of probability of error equal to 1 over 2 plus a square over n naught. So we need to see what this a square over n naught. It looks like a familiar function. The function of average SNR is defined as follows. SNR is equal to average received signal energy per complex symbol time divided by the average noise energy per complex symbol time, which is equal to a square over 2 divided by n naught, that is equal to a square over 2n naught. So hence, if we put this value in the equation we just found out for probability of error, what we get is that the probability of error is equal to 1 over 2 into 1 plus SNR. So for example, how do you compare this probability of error with the probability of error calculated for AWGN channel? Now probability of error, for example, you require is at 10 raised to the power minus 3. The SNR required for such probability of error would be approximately equal to 500 in linear scale and 27 dB in dB scale or log scale. If you compare it with PPSK, you only require 7 dB. So you can consider here that you required extra 20 dB of power to be sent from the transmitter by sending the signals at this power. This 20 dB is a lot of power. So to combat fading, we require a lot of power. Thank you.